So here we are going to solve another linear programming problem through the technique of dynamic programming. Consider the question: solve, maximize z equal to x1 plus 9x2 subject to the constraints 2x1 plus x2 less than or equal to 25, x2 less than or equal to 11, x1 x2 greater than or equal to 0. Now there are two stages for this particular question. Dynamic programming problem, you know, it's a multi-stage decision making process. The number of stages depend upon the number of decision variables. There are two stages depending upon the two decision variables x1 and x2, and there are two states. There are two stages and there are two states. The two states depending upon the two constraints, and the two states can be represented as b1 equal to represented by b1 equal to 25 and b2 is equal to 11. Okay, so this problem is a very simple one when considered through dynamic programming, and if you are doing the same with the help of linear programming techniques, you will have to write the initial standardized form. You will have to write the initial basic feasible solution, and you have to solve it through simplest algorithm technique through various iterations. So all those stages can be bypassed if you do it with the help of a dynamic programming problem, and it is very simple as well. So let us see how this can be done. So as in the previous problem that we discussed through another video, here also we are starting from the second variable or from the second stage, and so let us consider f2 25 11. So this is equal to maximum of 9x2, and that maximum ranges over the possibilities of x2 from 0 to b, where b is equal to the minimum of the x2 coefficients from the two constraints. So 25 by 1 and 11 by 1. So this minimum is 11, and so this b range is up to 11, and therefore we will write this as minimum of, so this can be written as minimum of 9 into minimum of x2. Minimum of x2 is 25 by 1, then 11 by 1. So this minimum value is 11. So 9 into 11, that gives 99. Okay, so that is the stage 2 f2 25 11. Now let us get to stage 1. So in stage 1 we have f1 25 11. f1 25 11 is a maximum of x1 plus 9x2. So let us write this as maximum of x1 plus 9x2 can be written as 9 into minimum of 25 minus 2x1. See how that x2 can be taken from the first expression. It is 25 minus 2x1, and from the second constraint it is simply 11, because the second constraint do not have any x1. Now the difference you can note in between the the second stage and the first stage. In the second stage and first stages, in the second stage we had only x2. So that is why we have the minimum considered over 25 by 1 and minimum considered over 25 by 1 and 11 by 1. But since we are in stage 2 we do have to consider both x2 and x1, we have to consider x1, we have to consider x2 in terms of x1. We are rewriting that minimum as minimum of 25 minus 2x1 and 11. Here we don't, in the second constraint we don't have any x1 coefficient, therefore 11 is enough for the second value. So hence we have this maximum ranging over the different possibilities defined as a function of x1. So here the range of x1 is from 0 to b. So here we shall have our B as minimum of 25 by 2, then 11 by 0. If you want to write it as 11 by 0, let it be there. So the minimum value is 25 by 2. So this x1 value range from 0 to 25 by 2. Okay, so we defined all the stages here. Here the problem, since the problem is a very simple one, we have only 2 stages. So we listed both the stages. Now let us try to get the minimum values. So we shall try to find the minimum values. So minimum 25 minus 2x1 comma 11. Let us find what this minimum value is. So the range of x1 is from 0 to 25 by 2. Okay, so let me write here, when x1 is equal to 0, the possible values are 25 and 11 and the minimum is 11. So when x1 is equal to 1, the minimum is 25 minus 2, which is 23, and the minimum between 23 and 11 is again 11. So how far this will go? This goes up to, say, x1 is equal to 7. So on it goes to x1 equal to 7. When x1 equal to 7, you will have 25 minus 7 into 2 equal to 14 and 11. So 25 minus 14 is 11. So 11, between 11 and 11, both the values are the same, and so the minimum is 11. Then when x1 is equal to 8, what happens is we will have 25 minus 8 into 2, it is 16 and 11. So among these two, between these two, 25 minus 16 is a minimum value. Okay, so from here the minimum value changes. From x1 equal to 8, the minimum value changes, and at x1 equal to 7, the minimum, both are minimum values. So let us write down this. So this is equal to, the minimum value is equal to 11 for 0 less than or equal to x1 less than or equal to 7, and it is equal to 25 minus 2x1 for a 7 less than or equal to x1 less than or equal to 25 by 2. Okay, so we can write the minimum in this way. Now let us find x1 plus 9 into minimum of 25 minus 2x1, 11. So this is 9, this is x1 is for 0 less than or equal to x1 less than or equal to 7. We have x1 plus 9 into 11, and for 7 less than or equal to x1 less than or equal to 25 by 2, we have the minimum value as x1 plus 9 into 25 minus 2x1. Okay, so minimum of 25 minus 2x1 and 11 is obtained in the previous stage, and add that, multiply that minimum with 9 and add that to x1, so that we will reach this particular step. Okay, now let us find the maximum among these possibilities. So we got all the minimum values, and let us find the maximum among these possibilities. Now, so we have two options. One is x1 plus 99, and the other function is x1 plus 9 into 25 minus 2x1. Okay, so between these two possibilities, this attains its maximum at x1 is equal to 7. This attains its maximum at x1 equal to 7, because x1 equal to 7 is the maximum attainable range. So at x1 equal to 7, this becomes 99 plus 7, it is equal to 106. And here that x1, in the second part of this expression, x1 is subtracted. Okay, so the second part also attains its maximum at x1 equal to 7 or at its lower value. So here also a maximum is at x1 equal to 7, and that maximum value is 25 minus 2 into 7. So 25 minus 14, 11. 11 into 9, 99 plus x1. That maximum value is also equal to 6. So let us conclude our F2 25 F1 25 11. So we are at our F1 25 11 is equal to the maximum value and the maximum value is 106, or we can write it as maximum of 11, maximum of x1 plus 99, comma x1 plus 9 into 25 minus 2x1. So we found that maximum value right now, and this maximum value is 106, and that is obtained by taking x1 is equal to 7 and x2 optimum. So for optimum, let me write as superscript O, and x2 optimum is minimum of, x2 optimum is a minimum of 25 minus 2x1 and 11. 25 minus 2x1 at x2 equal to at x1 equal to 7. At x1 equal to 7, it is 25 minus 14, it is 11, and hence x2 optimum is equal to 11, and therefore we get maximum Z is equal to 106. So this is how we proceed with dynamic programming technique in order to solve the linear programming problem. The given problem is split up into two stages. Here we have stage 2. This is the second stage which is considered first, and this is the first stage which is considered as the second one. We are proceeding through the backward computation method. So here we have f2 first. So in f2 we will consider just the variable x2 and we find its optimum value, and then we proceed to find f1 2511, where we concentrate on x1 and we find maximum of x1 plus 9x2. The whole objective function is considered. x2, its optimum value is obtained from the previous stage as minimum of 25 by 11 and 11. So this 25 should be modified so as to include x1 as well. So 25 becomes 25 minus 2x1 comma 11. So by using that and hence finding the minimum of 25 minus 2x1 and 11, we proceed to find the final optimum value. Thank you.